Entropy as a measure of surprise. A fundamental concept in the study of information entropy is the surprisal of an event, also called itself information. The surprisal of an event measures the amount of information gained when the event occurs. It also measures the surprise associated with the occurrence of that event. We have already learned how to calculate surprisal quantities for a discrete random variable. It is simply the amount of information we gain when observing the outcome of a particular event for the random variable. Formally, for a discrete random variable x with n possible values and associated probabilities, the surprisal, that is, self-information of the event that x takes on the value x sub I, is log base 2 of 1 over p sub I, where surprisal is measured in bits. These are the same bits we have been using all along. More generally, the surprisal of an event with probability p is log base 2 of 1 over p. Since the surprisal of an event is simply the information content of the event, all of the insights we have gained so far about information content are relevant to the concept of surprisal. This includes our interpretation of Shannon entropy. Recall, the Shannon entropy of a random variable x is a measure of the expected surprisal of the random variable. In other words, entropy is the average surprisal of all possible values of x. Question: what new perspective comes from calling the information content of an event surprisal, or from viewing the entropy of a random variable as a measure of expected surprisal? Answer: these new names tap into the human psyche by evoking a visceral response to otherwise cold, austere calculations. When an unlikely event is observed, we associate it with a high amount of information and surprise, whereas when a more likely outcome is observed, we associate it with a smaller amount of information and surprise. If the probability of an event is 1, then the event is certain. In this case, there is no surprise upon learning that the event occurred. And likewise, we receive no information from knowledge of its occurrence, since we knew the event would occur. So the surprisal of such an event is 0 bits. On the other hand, if the probability of an event is near 0, then the event is very unlikely, and we would be very surprised to learn that the event occurred. In this case, we receive a great deal of information upon learning of its occurrence. Hence, for this event, the surprisal is large. In the intermediate case, when the probability of occurrence is 0.5, both the occurrence and non-occurrence are equally likely. In this scenario, we receive exactly 1 bit of information upon learning the event occurred, which means that the surprisal of the event is 1 bit. Thus, 1 bit of surprisal is what you feel after calling heads on a fair coin toss and then watching the coin land heads up. You experience 2 bits of surprisal when seeing your prediction come true that 2 randomly tossed coins would land heads up. 3 bits of surprisal is probably enough to make people smile when you correctly predict that the 3 coins will land heads up. 10 bits of surprisal will elicit gasp of incredulity from witnesses seeing 10 coins landing heads up that you predicted ahead of time. 15 bits of surprisal would be the degree of utter surprise and delight a student would experience who had forgotten to study, but nonetheless correctly guesses all of the right answers on a 15-question true-false quiz. 20 bits of surprisal is what a person feels when winning the lottery or being struck by lightning. The surprisal perspective has the following benefits, among others. 1. It transforms the probabilities of rare events into more manageable quantities. 2. It relates the numerical calculation of the information content of an event to the degree of surprise you would experience when tossing a corresponding quantity of coins and watching them all land heads up. 3. It creates a common scale for comparison among probabilistic events, provided the events have known probability. 4. It cultivates a more intuitive and objective understanding of uncertainty. Surprisal of landing all heads. Please reflect upon the increasing surprise you would feel after calling heads for the fair coins within each group, and then watching all of the coins in that group randomly land heads up. Pause for a few seconds on each group until you get a visceral sense of what surprisal, measured in bits, actually means. Surprisal of 1 bit, surprisal of 2 bits, surprisal of 4 bits, surprisal of 8 bits, surprisal of 16 bits, surprisal of 32 bits. And the surprisal of 64 bits. A surprisal paradigm has great potential in a society awash in statistics, many of which consist of numbers, charts, and graphs that convey little to no meaning to the average citizen. Indeed, statistical data are often misunderstood and sometimes egregiously misinterpreted. Even ordinary percentages pose a challenge for some who struggle to make sense of fractional quantities. In such a world, a mutual frame of reference for interpreting statistical calculations of risks, measured in bits of surprisal, could help people develop an intuition and visceral sense of the meaning and significance of probabilities within diverse contexts. Perhaps the vociferous vaccination controversy would quiet down if everyone had a closely shared understanding of the rates of adverse vaccine reactions. More generally, the use of surprisal estimates in communicating medical risks would help patients make more informed choices among treatments and procedures that have small but non-trivial chances of dire outcomes. Furthermore, if surprisals were used in determining the degree and nature of the monitoring of patient care, costs of medical malpractice might decline by reducing the need for legal redress. Indeed, when assessing risks with known probabilities, a person could easily interpret the surprisal value of a given risk by considering the chance that tossing an appropriate handful of coins will or will not result in all heads. This might sound subjective and non-rigorous, but it could empower many who have difficulty deriving meaning from probability calculations devoid of physical or tactile experience. To end this section, I highlight two fields of active research that rely heavily on the principles of information theory. The first is called Surprisal theory, which is a theory of sentence processing. The second is called Surprisal analysis, which applies principles of maximal entropy to engineering and the physical and biological sciences. Surprisal theory. Surprisal analysis. Is information and entropy the same thing? John von Neumann, the father of the modern computer, is considered to be one of the greatest mathematicians and physicists of all time. When he was 6 years old, he could divide two 8-digit numbers in his head and could converse in ancient Greek. When the 6-year-old von Neumann caught his mother staring aimlessly, he asked her, "What are you calculating?" He made major contributions to a panoply of theoretical and applied areas. Claude Shannon recounts a conversation he had with John von Neumann about what to call the foundational idea that would underpin the entire field of information theory. Quote, "My greatest concern was what to call it. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. When I discussed it with John von Neumann, he had a better idea. He told me, you should call it entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name, so it already has a name. In the second place, and more important, no one really knows what entropy really is. So in a debate, you will always have the advantage." When John von Neumann declares that no one really knows what entropy really is, it reveals the difficulty of answering a question such as, are information and entropy really the same thing? Setting aside the virtual impossibility of resolving this question to the satisfaction of every practitioner, we will try to make some progress in that direction. To begin, we should note that there is an ongoing debate whether there is an actual correspondence or equivalence between thermodynamic entropy and information entropy. Ultimately, the criticism of the link between the two notions of entropy is a matter of terminology rather than substance. Neither side in the controversy will disagree on the solution to a particular thermodynamic or information theoretic problem. Moreover, in ideal circumstances, a single bit of Shannon information really does correspond to a reduction in the entropy of a physical system. Stephen Hawking often spoke of the thermodynamic entropy of black holes in terms of their information content, framing such questions as, do black holes destroy information? There appear to be deep relations between entropy of a black hole and information loss. So, in what sense are information and entropy equivalent? They are two sides of the same coin. The coin being observation. Entropy is a measure of uncertainty before you flip a coin or make an observation. Information is a measure of knowledge gained after you flip a coin or make an observation. Although information and entropy may not actually be the same thing, they do represent the same quantity from complementary perspectives. Final observations about information, entropy, and surprisal. The formalization of information departs from the more usual notion relating to semantic meaning. Although information can be described as the resolution of uncertainty, the technical definition for the information provided by some event relates to the probability of occurrence of the event. In information theory, one bit is defined as the amount of information contained in a binary random variable, that is 0 or 1, with equal probability. In other words, one bit is the quantity of information gained when the value of such a random variable becomes known. The entropy of a random variable is determined not just by the number of different values the variable can take on, but by the probability distribution of the variable. Recall that the entropy of a random fair coin toss is 1 bit, whereas the entropy of a random weighted coin toss with probability of 0.75 and 0.25 for heads and tails respectively is only 0.81 bits. Furthermore, since entropy is expressed in terms of probabilities, it depends upon the knowledge of the observer. One person may have different knowledge of the system than another, and therefore would calculate a different numerical value for entropy. A similar conclusion applies to the surprisal of an event, which is a measure of the surprise generated when the event occurs. The smaller the probability of an event, the larger its surprisal. Yet, if one observer possesses greater knowledge or can perceive hidden structures and relationships, then that observer will be able to predict the outcome of an event that generates tremendous surprisal for virtually everyone else.